Hey there, and welcome to your Unit 6 Part 2 video review. This is covering non-renewable energy. Now this is, when you take a look at this, quite a goodish number of slides. It's, let's see, 89 slides to get through, so there is a considerable amount of stuff going on here, but here's why. Non-renewable energy resources, as well as being sources that are used most often in developed countries, also happen to produce, the most pollution. So the impacts of using these resources are considerable. So we're going to be going through all of the ins and outs of all of this. Again, a lot of this we went over already in class before we started staying at home, but there's part of it that hasn't. So this is really where you need to start perking up and paying attention. So let's go ahead and do this thing. All right, so again, I'm going to start every topic off with the course and exam description stuff you should be focusing on. Again, if you're not looking at this, you're really doing yourself a disservice. If you look at this list, if College Board took the time to specifically note out of all of the harvesting methods that are out there, they specifically talk about fracking and how it causes groundwater contamination and the release of volatile organic compounds, probably something that you're going to want to know. So again, make sure that if I don't address these super specifically, and I really think that as we do our review, I am going to just literally go down this list, make notes for yourself. Okay, so again, remember where coal, oil, and natural gas came from. Remember what anaerobic means. It means without oxygen, so that means instead of aerobic conditions like, let's say, combustion, instead of producing carbon dioxide, it's producing methane, and which is natural gas, and then also changing those carbon compounds that are found in the dead plant and animal matter into these three. Remember, again, we're talking about coal, oil, and natural gas here, into these three fossil fuels. All right. Is this something that I would necessarily see being asked on the national exam? No, just be aware again that it's heat and pressure. And where does some of that pressure come from? You're not going to have bituminous coal forming at the surface of the planet. That's going to have to be where this stuff is migrated down, down, down. Something interesting to think of is why is it that you've got all of this oil forming at the bottom of the ocean? Think about how much that water weighs in terms of pressure. Excuse me, let me get a drink here real quick of coffee. Okay, so remember again, you definitely need to know the difference between complete combustion and incomplete combustion. Why do you care? Because carbon dioxide is bad enough. We're going to talk about very briefly what a greenhouse gas is. Just realize that CO2 is on the list of compounds that when it goes into the troposphere provides an additional layer of insulation and keeps Earth warmer than it needs to be. Incomplete combustion is where you create that carbon monoxide. That's the stuff that can bind to human hemoglobin, making it harder for it to uptake oxygen, which is, bad. All right. The only reason for this slide is so that you understand while combustion and aerobic respiration are both similar in the products that they put out, it's the timing of them. It's why you're not catching on fire, basically. So this is not something that would appear in the national exam. This is just so you understand the difference between these two. And again, it is important for you to understand not only what incomplete combustion forms, and incomplete combustion usually occurs when there's either not enough oxygen or it's not burning hot enough. All right. So again, will you have to know these specifics? No, except for this last one. Okay, combustion in general is, not good. You've got to kind of look at the products there. All right, so we talk about coal being the dirtiest of fossil fuels. You need to understand what that word dirty means. Dirty means that When it combusts, it produces more pollution than the other types of stuff. When you have something solid and it burns, you're always going to have particulate matter. That's just kind of the way that it goes. So you don't see that as much with oil, and you certainly don't see it at all with natural gas. There are also a ton of impurities in coal that you cannot just wash away. You need to know that coal contains a lot of sulfur. You need to know that coal contains traces of mercury. It's also been known to contain other heavy metals like arsenic and lead. It can contain nitrogen. Now, why do those things matter? Because when sulfur and nitrogen are combusted, they form gaseous products, which we've talked about in Unit 7, that can then lead to other problems. And then heavy metals, when they are vaporized, can be breathed in by humans, stored in the fatty tissues of the brain, and then lead to everything from delayed development to permanent learning disabilities to, in the case of mercury, you've got things like adult onset heavy metal schizophrenia. Okay, however, there is a lot of stuff, this stuff around. The United States happens to be sitting on the largest coal reserve, so guess what we use here in the United States to create electricity? This. Plus, think about let me see if we actually have the pros here. I'll get to the pros and the cons here in a second. All right, when you are looking at this, again, you want to look and say to yourself, where is heat lost, so that you can understand efficiency, and then where is the pollution? There are actually three sources of pollution here. So let's go ahead and talk about that. So anyway, I think you guys know by now, you burn the coal to boil the water to create the steam that turns the turbine, that turns the generator, that creates the electricity. Everybody knows that. Side note, take a look at the water that's being boiled to turn this. Notice that's a closed loop. Okay, that water is endlessly condensed and then returned into steam. How do you do that? Coal-fired power plants all sit next to a water source, and they pull that water in like a separate loop. If you take your fingers and you make two OK signs, but then you make those two OK signs where the two O's make a chain, that's kind of how this works. And if you pull it together so that parts of your fingers are touching each other, that's kind of how this is. Where the two pipes have not necessarily physical contact, but where they have contact with each other, the cold river water heat goes from this hot loop into the cold river water, and then it's spat back out. So this is the first form of pollution, thermal pollution. This is absolutely necessary, or this whole thing would overheat and you could literally have it blow up. How does it blow up? Remember that when water expands, it does so very quickly, and if it doesn't have anywhere to go, pressure builds up and it makes a place for it to escape. So first place you have pollution is right here, thermal pollution. Second place you have pollution is when you burn stuff, you create particulate matter, and then also gaseous products. It can be carbon dioxide, carbon monoxide, sulfur dioxide, the NOx twins, NO and NO2. You have all of that stuff being released, and if you don't have anything to deal with it here at the top of the smokestack, it just comes out. In Unit 7, what happens to all of that air pollution is discussed in detail, and how it affects human health systems. Remember, if you have air pollution, it's going to affect the parts of the human body first that have to do with the air. In other words, the respiratory system. Now, obviously, anything you breathe in is eventually going to affect the rest of your body, but respiratory system is always a great place to start in terms of human health effects. And remember, it also affects plant life and all that stuff that's talked about in Unit 7. So that is the second place that there's pollution. And then thirdly, when you burn things, you always have ash left, and you've got to take it somewhere. Now you have, if it's got impurities like mercury in it, you can't just take it to a landfill. You have to take it to a place called a secure landfill, which means it's like a giant vault where you just put stuff that you don't want to mix with anything else. So you're creating basically this crypt of stuff that you can never release back into the environment because it's concentrated toxic material. So there's all of that. Now, in terms of efficiency, think about all the places you're losing heat. You're losing heat to this cooling here. As mechanical things move, you're losing heat to friction. When electricity gets pushed through wires, you're losing heat to resistance. So you have to imagine that the amount of energy that is straight up in this coal is not going to be the amount of energy that comes out here and charges your phone. Also, think about how this coal got here in the first place. You had to have a mine over here where you dug it up, and you used fossil fuels to power the tractors and things that dug it up. And then you have the transport to the processing plants, and then you have to bring it here to the power plants. So there's this whole other place here where you're using energy to harvest energy. Remember the EROEI of it all? That's happening largely right over here. So again, this is not just about burning the coal to boil the water to turn the turbine to create the steam. Let me start again. I just messed up my own thing. You burn the coal to boil the water to create the steam that turns the turbine, that turns the generator, that creates the electricity. That's the smallest part of a diagram like that. Look for all of the other things. Okay, so moving on. Again, this is all the parts. All right. So we've already talked about the types of coal. Obviously, the farther you move from left to right, the more desirable the coal is. Turns out most of the coal on this planet is right here in this category, bituminous. These are all the places where you have coal in the world. One of the things that we'll do to get you ready for the national exam is we'll create a very exhaustive map. Although it looks like there's a lot of coal up here, which there kind of is, the biggest proven reserves are here in the United States. All right, so here's all of this stuff. Oh, side note, if you look at where a lot of this coal is, you're going to notice it's right up against mountain ranges. Okay, so what are the advantages to using coal? There's a lot of it. It's super easy to get to. You just dig it up. We don't have a lot of subsurface mining these days. And then it's solid. You just let it sit. In terms of polluting the environment, yes, you have problems when it rains on this stuff. Yes, you have problems with the tailings and the spoils and water running through that, and acid mine drainage is still very much a thing. But the coal just sits here. You don't have coal spills. You don't have coal seeping into water supplies. Yes, you can have water run through it and take it into the water supply, but when you compare this to, say, an oil spill, it's not the same thing. And then again, it's a solid. It's not hard to transport, and you don't have to do a lot to it. It's ready to go. Here are the disadvantages. Again, we've talked about tailings and acid mine drainage, and then just all sorts of other impurities that are in that stuff. This is a big concept. Make sure you spend a goodish amount of time with acid mine drainage. So basically, here's what happens. Water leaches into the mine. Remember what leaching means? It just means water runs through a place and it picks up ions. So there's something called pyrite that's in most discarded piles of stuff from mining. Why is that a problem? Because it contains this stuff right here, iron sulfide. I guess iron 2 sulfide, but just pyrite for you. You don't have to understand what that is. Oxygen and water obviously are everywhere. So why is this a problem? There are actually three actual problems with this. So the first one is iron is a toxic heavy metal. So it builds up in fish, and it can kill especially the apex predators. Here's the other issue. This reaction produces H+, which for those of you who haven't had chemistry, is the ion and acid that makes it an acid. So, first problem, you're suddenly reducing, remember, runoff is a thing. So you're suddenly reducing the pH in aquatic systems. And that sudden change, remember, could be on the fish's range of tolerance and it kills them. Here's another problem. As this acidic water washes across ground between these tailings and spoils to get to the river, it will dissolve other metals and bring it along with them. And so those are then transported into the stream where they can, again, be toxic to the fish. Please be careful using the word toxic on the national exam. What that means is that they will exist in high enough concentrations to be deadly to the fish. Not killing all of them, but definitely impairing their ability to live their normal lifespan. Okay, air pollution. We've talked about all of this already. And again, even when you have complete combustion, you have a lot of carbon dioxide being released, and we will get to climate change. And then residual ash. Talked about that as well. All right, so let's talk about petroleum. What does it mean to be cleaner? It means you have fewer impurities, especially since this has to go through a refining process. You could pull out a lot of the sulfur. Not as much the nitrogen that's in there, but a lot of the sulfur. There's not going to be the heavy metal component that's in there. But here's an issue. Keep this in mind. It is a mixture of hydrocarbons. The stuff that you put in your car is going to be different than the stuff that we put into jets. All of that is all mixed up together. It's like getting a bag of beads and they're all different colors and you use the purple over here and the blue over here. They have to be separated. We'll talk about that in a second. Now again, its fluid nature means that you can use this in vehicles. You know, nobody is using a coal-fired furnace in their car. All right, so again, do you have to know this is specifically algae? No. Do you realize, though, that this is, it's not like you have bubbles of this stuff sitting around. It is usually in pores. So that means you're kind of, it's more akin to drinking soda out of a drink that has a lot of ice in it. It's that same idea. All right. So petroleum is easier to get to because think about it. We harvest a lot of our oil from the ocean floor. There could be a ton of coal miles under the ocean floor. We would never know it, nor would be able to get to it because we can't dig down and get it. Really, all you have to do with oil is find a big pocket of oil where a lot of it is congregated in those pores in the rock. Like a Capri Sun, just kind of punch a straw in there and just let it flow out. And side note, while I've got you on that, that's how oil drilling is. You punch a straw into it and it will gush on its own. But eventually the pressure equalizes to the outside, and then that's where you have to start applying some sort of mechanical vacuum to suck it out. And then at some point, just like when you get to the bottom of your cup of soda at a restaurant, there's nothing left and you have to move on. Okay, so a lot of this is transported by either pipeline on land or supertanker in the ocean. We're going to get to why that's important. Guys, when it comes out of the ground, it's super sticky and looks like that. Oftentimes it's found with the natural gas in pockets above and in the petroleum. Okay, the refining process is where you separate the different hydrocarbons. The way that you do this is through something called distillation, and here's how distillation works. You slowly heat something up until a vapor comes off. You collect that whole vapor, because that means one component in the whole thing is boiling and the rest of it is not. Once the vapor stops coming off, as you hold it at that temperature, you then slowly heat it again until another vapor starts coming off. You hold it at that temperature until you collect it all, and so on and so forth. And then you can condense that vapor and get what you need. This is how, if you've ever heard of a moonshine still, it's because drinking alcohol before you can drink it safely has to be distilled so that you can get impurities off. And you do the same thing. You boil, not boil the liquid, because then that means that everything's coming off at the same time. You gently heat it until one thing comes off and you collect that, and so on and so forth. Um, anyway, so that's how that works. Um, Oil refining is not cheap. Also, again, some of these facts that are up here, please don't frantically write those down. This is not that kind of party. That's just for you to go, huh. So when you hear if barrels of oil are referenced on the national exam, you kind of have an idea in your head of what that looks like. All right, so here is where you find oil. Realize that this up here in Canada is tar sand. Okay. This is an article about tar sands. If you want to read a little bit more about it, you're welcome to. But basically, why is this a problem? Because you've basically got to scrape it out of the earth and use a ton of water to even get the oil out of the sand and rock that it's in. It turns out that we have tar sand refining plants down here in the United States. We will talk about how that's transported. Obviously, when you're, just like with coal, when you're scraping stuff out of a large place, you have habitat destructions. If you remember that HIPCO, habitat destruction, you have invasive species can come in by all of the roads that you build to get in there. You have loss of biodiversity, creation of pollution through the harvesting process, blah, blah, blah. All right, so what are the advantages? The obvious here. It is, why is it cleaner burning? Because again, you have less impurities, and then you also have more complete combustion that happens. And then also, because it's energy dense, it means that you have to burn less of it to get more energy. Let's see what else. Disadvantages. Definitely know you still have some of these trace metals, but it's, it's still not as much as it is in coal. And I know this says sulfur, but again, it's still not as much as you see in coal. Nitrogen is NOx is more associated with this. Potentials for leaks and spills. Guys, when you transport things by pipes, they leak. When you transport things by super tanker, they crash and can break open like an egg. This stuff is bad for animals, and here's why. When you ingest it, it is a poison, and it builds up. It's not good. And then when you talk about things like birds and animals with fur, it coats their feathers and fur. Air pockets are what keep animals warm, not the fur and the feathers themselves. The oil destroys those air pockets, meaning that animals die of hypothermia. And then also the act of preening the oil off of their fur and feathers means that they're also ingesting it and can die that way as well. Plus, in the case of birds, oil is heavy and it's sticky. And if it sticks to the birds, it also means they can't fly. Okay, so habitat destruction. Again, take a look at this. Another thing this is doing is it cuts through a lot of Native American historic land, and pipes leak. They just do. And so that means that you have not only an opportunity for animals to become directly affected by it, but you also have to think, what also is occurring here in the Midwest. Remember, the Ogallala Aquifer is over here. So you also have this opportunity for oil to seep into groundwater supplies. Gas flares. This stuff is really, really flammable, and it just takes a spark for it to light on fire. Okay, so here are some disasters that are in controversies that are kind of linked to this. Exxon Valdez. This was in the 80s. Dude was literally drunk, crashed onto a reef, thing broke open. 11 million gallons of oil. There are still tar balls of this stuff washing up on shore to this day. If you're wondering what this guy is doing here, these rocks are not black. they are covered in oil, and he is having to power wash every rock. And it's one of those, sometimes the cure is worse than the disease, because basically anything that was surviving on there is just getting blasted off. Why are they wearing the suits that they are? Oil is toxic to humans as well. So, and the stuff is sticky. They had to clean every single individual rock that was on here. This accident is why all ships that carry oil are now what's called double hulled. The hull is the bottom of the ship, and now all of these things have two of them. So if the outer one breaks, the inner one stays intact. Anwar is a fight that's currently going on right now. There is currently oiled fields right outside of this National Wildlife Refuge. There are exploratory drillings going on just outside of it. There is some indication that there is oil underneath the refuge. What are the pros of tapping into it? We don't need to depend as much on outside sources of fossil fuels. The cons are, of course, this amount of oil won't last very long, so why destroy this refuge of unique animals here in the tundra, plants and animals that are here in the tundra in the first place. Deepwater Horizon. Okay, this is something that happened just off of our coast. This happened in 2010. Basically, here's what happened. Offshore drilling, a pocket of methane, natural gas, got caught in the pipe as it was being pulled up. The gas expands as pressure is reduced, and so that partially blew the pipe. There was a spark, and then the thing just blew up. Here's the problem. Because that straw that was pumping out the gas broke off underneath the water, it just kept pumping petroleum for 87 days. Also the problem with this is that BP, it took a lot of doing to force them to admit that things were as problematic as they were. Now, why not just quote unquote shut this off? And the answer is, I don't know if you've ever tried to, you can go outside, turn on the hose outside, and then try and take a cork and stuff it into the hose while it's going at full speed. It's kind of tough. So it was a whole engineering process to get this thing to be plugged up and just stop gushing oil. Also, just real quick, how did they clean this up? Remember, not all of the oil floated to the surface. Some of this oil is heavier than water, and so just pockets of it drifted all through the Gulf. And so that also meant things like shrimp and oysters, which are things that Gulf fishermen harvest, were not accessible for years. So that meant that families that depended upon that source of income were out of luck for a little while. They actually had to light some of the oil on fire because it was the quickest way to pick this stuff up. Natural gas is the cleanest of the three fossil fuels because it burns the most completely. It also has the fewest impurities in it. And you usually find it with petroleum. There are times that you do find pockets of natural gas in coal mines, which was how some of those subsurface mines ended up blowing up, because when you tap into one and the act of tapping creates a spark. This is also back in the day when you used to use candles to be able to see by. You also find it separately. Please remember that the quote-unquote acting ingredient is methane. You also have ethane, propane, and butane in there. Obviously it's a gas, so it's lighter than oil. Duh. How do you use it? All of these things. Advantages. It's pretty much ready to go with very few impurities when it comes out. Again, really concentrated energy, doesn't produce as much CO2 as coal. You can shunt it through pipelines. You can even condense it and transport it as liquid. Disadvantages. Methane itself is a greenhouse gas, and it will escape and contribute to climate change. So, yeah. Why bring this up? because also remember that beef animals also produce a lot of methane, whether they're grass-fed or not. So the more meat we eat, the more we're contributing to climate change. We talked about this in class. I'll talk about why fracking can lead to groundwater contamination, release those volatile organic compounds. Here's why. Okay, so you drill a well down and then you drill horizontally. You fill that with high pressure water, sand, and then other proprietary, meaning I can't tell you about it because I don't know, components that keep this thing kind of moving and fluid. And by building up liquid in here, you create a pressure that fractures the rock around it. And basically what that does is the itty bitty little pockets of natural gas that are here open, and the gas races into the same line, and then you can harvest it this way. Some of the stuff that is in there are volatile organic compounds like benzene. What does volatile organic compounds means? Volatile means that they become a gas easily. Organic means lots of carbon in it, and then compounds are just more than one atom in there. Okay, so that's pretty much how it works. Now, this is the water table. This is a confined aquifer. Of course, the drilling companies are like, well, we're nowhere near this, but remember, you cannot predict how fractures work. Plus, you also have this pipe right here that can't allow volatile organic compounds into the air. Okay, so again, this is literally what I just talked about right here. All right, so how do we extract oil? I kind of talked about this already. Big pocket of oil concentrated in porous rock. You punch a straw into it. Initially, it just comes pumping out by itself, and then eventually you have to apply a vacuum like drinking out of a cup. When the cup is empty, you move on. Or what you can do is you can take water and pump it down here and then suck it out again. Please realize, again, the thing you also need to realize is not only do you have habitat destruction and all of that stuff, you are also using a heck of a lot of fresh water to do this harvesting process, which means, I mean, think about how much fresh water we have on this planet. Not much. So there's that as well. We went over mining already. Okay, we already did this. Anyway, you may want to spend a minute with this particular slide so that you are able to talk about impacts, both direct and indirect, on the environment in terms of all different sorts of harvesting of fossil fuels. So this is not L, by the way, that's EI, that's energy intensity. So this kind of just tells you why it is that we use certain, why we use fossil fuels in certain places as opposed to others. Okay, this is, I don't know if we're going to have to know who Hubbard is, but he's a dude who basically predicted that we might be at peak fossil fuel production and then it might be downhill from here. In terms of being able to harvest this stuff. If it's a non-renewable resource, it's going to run out at some point. We may as well plan ahead, and we'll talk about that when we get to renewable resources. Something for you to ponder here. I'm not going to spend a lot of time on this. Okay, nuclear power. Definitely read through all of this stuff. You can see there are a lot of very specific facts that we have to know. You are going to need to be able to calculate half-life. That will be in a separate... Oh, I found a spelling mistake. That should say which are. Anyway, you'll learn how to do half-life. Alright, so the word fission means to split apart. So how does this work? You take a neutron, which is a subatomic particle, and you basically throw it at uranium. Uranium is already unstable. It's barely holding itself together, and it cracks into two smaller components, and then it sends more neutrons. This right here that you see is a release of heat energy. And then you have this chain reaction that occurs. What you're seeing here is an uncontrolled chain reaction. This is what an atomic bomb looks like. When you, and it's an exponential function. When you take out multiple neutrons at every stage of this, you create a more linear, controlled release of energy, which is what happens in nuclear power plants. I always find this funny that we harness the might of the atom, the energy that holds our very atoms together, and we use that energy to boil water. All right, so we use that energy to, shocking no one, boil water to create steam that turns a turbine, that turns a generator, that creates electricity. Uranium contains orders of magnitude of more energy than coal does, which is why it is used. So yeah, it's powerful stuff. I'll get to some of the cons here in a second. This should look shockingly similar to a coal-fired power plant with a couple of big exceptions. If you remember, there were 2 loops of water. Here you have 3. The first loop of water that you have is associated, so instead of burning something, here is where you're cracking atoms apart, and you have this first loop of water. It is completely contained within, you can see this tan facility. That is the nuclear power plant itself. Why is it contained? Because, one of the things this also releases is, radiation, which doesn't create superpowers unless you want your superpower to be to die almost immediately. So this whole thing in here is radioactive, and so it's pretty much sealed off from anything. Then you have this second completely closed loop of water that takes this heat, and then this is the thing that turns the turbine, that turns the generator, that creates the electricity. This is still so freaking hot that you need a third loop of water that is coming from an outside water source to cool this whole thing down. So that means that these things can only be built when they're next to a river or a lake where you can draw water in to cool it down. So, fuel rods, reactor core is basically where all the radiation happens. Fuel rods are where where the uranium actually is. These are all the parts that we talked about. Okay, so what is in there? Obviously, he's not holding an actual fuel pellet of uranium. Duh. Now, this is not how it comes out of the ground. We'll talk about how that is formed in just a minute. All right, control rods were those things I was talking about that remove enough neutrons from the process to make this a linear and controlled release of energy rather than a exponential release of energy. Exponential releases of energy are bombs. Now, as scary as this sounds, we have only had 3 nuclear-related disasters in the history of using this stuff. Now, there are other cons to building nuclear power. The fact that they could potentially blow up is not one of them. The risk is actually pretty incredibly low because of a lot of the redundancies that have been built into these things. All right, so those are what control rods are. That's literally what it says. They control the pace at which the nuclear reaction takes place, which controls how much energy is released at one time. Okay, so the biggest problem, though, when those disasters do take place is that you're releasing energy. Now, think about what's also happening here. You have this buildup of steam. So it's not that you're just releasing energy and it's kind of floating around. It is exploding out with this radioactive steam that can then go into the upper troposphere, where you have jet streams of air that can take it to lots of other places, at which point that radioactive water will condense and then fall. This is what's called nuclear fallout. So it means that a disaster in one place becomes a disaster that happens in a lot of places. Okay, so how do we get those pellets? Well, we got to dig up a lot of ore to condense. So the act of finding enough uranium to run these things is a destructive process in the first place. But here's the mitigating factor. You don't need as much of it to get the same amount of electricity as you do with coal. So yes, while you're still digging this stuff up, it's not as much. All right, Please note all the places where you find. This is not where the stuff is used. This is where you dig the stuff up. Okay, Canada and Australia are our two biggest suppliers of uranium. Kazakhstan. Oh, South Africa. Very nice. Okay, so here is the biggest advantage of nuclear energy. There is no pollution at the plant except for thermal pollution. There is no air pollution. There's no ash produced. Now, you do have the leftover, they used uranium, which is radioactive for basically ever. We'll get to that in just a second. Why do places like Japan depend upon nuclear power so much? They use a lot of coal, but they've got a lot of nuclear power plants over there because, remember, it's a tiny island and you can produce a lot of electricity from not a lot of fuel and from a smaller power plant. It's again very predictable when you compare it to wind or sun. Okay, what are some when things go wrong, they go very, very wrong. Also, there comes a point in time where the uranium is no longer producing enough energy to boil that water, but it is still producing plenty of radiation that will kill people for basically ever. So what do you do with that stuff? We'll get to it in a minute. Let's go ahead and talk about some nuclear disasters first. There's 3 that you need to know about. The first one is one that happened here in the United States. 3 Mile Island. By the way, side note, what you're looking at right here is steam. It's not smoke. All right, and the reason that they have this plant here is because they have all this water to pull from. These are all called cooling towers. This little guy right here, that's where the nuclear power plant is happening. So there was a cooling water valve mishap, and there was a release of radioactive steam. The issue is, though, that as soon as this happened, immediately everyone was evacuated from the area, and although it's very likely that infant mortality and cancer rates went up, a lot of that was mitigated because, number one, the explosion was caught, the problem was caught early, and then number 2, people were told about it right away. Now, why is there infant mortality? Remember that infants, because they're so small, it takes, let's say there's 20 grams of this stuff floating around. It may only take per unit, because they're smaller, that means that it takes less amount for there to have a toxic buildup per unit volume of an infant than it does for people. It's why that when you look at the back of medicines, you have different doses for different ages. It has less to do with your age and more to do with your body mass. Also, do realize that when any sort of toxin is taken into the body that is not filtered out by the placenta, in pregnant women, it also affects fetus development. Okay, Chernobyl. Same idea, worse outcome. Major explosion. 10 days. For 10 days, a local government did not tell people in Chernobyl that there was a problem. Most of those people died, even though they were taken elsewhere after that 10 days. And then there was a ring of cancers that occurred for a decade after that explosion, because of the nuclear fallout. Okay, and then we just had Fukushima. Japan is an island, duh. And so where they set this thing up was next to a body of water. There was a tsunami that came through and basically cracked these things open like an egg. Units 3 and 4 are still shooting out radiation. I do need to post for you guys a video on tsunamis. I didn't really go over that very well the first time. Okay, so here's all the stuff that happened. Please remember what a tsunami is. This is where you have an earthquake. And remember, Japan sits on the Ring of Fire. Earthquake, The tremors translate to the water, and it's not a cresting wave. It's literally a wall of water that can go for a mile more inland, destroying everything, and then pulling all of the whatever the impurities it kicks up back out into the ocean again. Okay, so what do we do with the radioactive waste from these things? Basically anything that comes in contact with these plants eventually does become radioactive. So what do we do with all this stuff? Oh, by the way, here's how. Half-life means how long does it take for half of this to no longer be radioactive? 704 million years. Uranium has to go through multiple half-lives in order to no longer be radioactive enough to hurt people. Okay, so there's, what I just said. This is a kind of math that we will go over in a separate video. I'm not sure whether or not you have to use this equation yet, which is why I'm not talking about it. Do realize that we use radioactive elements all the time. But if something's only radioactive for a few minutes and it's a low-level radiation, it's not a big deal. It is massive amounts. It's like the sun. The sun is radiation. Same idea. So if you're wondering who these people are down here, this is Marie Curie right here, who won a Nobel Prize for her work on radiation. You don't have to know that for the exam. That's just a cool fact. It's also the thing that killed her. Are these units that you need to know? No, but this is also why I tell you about this, because this is her right here. I'm assuming Becquerel is one of these guys. I'm also assuming that this is Marie Curie's husband, because, side note, her first papers had to have his name on them because nobody wanted to listen to a lady talk about science because, you know, lady. Okay, so this stuff, I'm going through it very fast because I'm going to teach you how to do this in a separate video. Let me just go back real quick and just show you something. I'm fairly certain you're not going to have to use this formula because any calculator you need says a 4-function calculator will be fine. So I'm going to teach you the way to do half-lives where you're kind of approximating things. So if you can divide by 2, you're in good shape. For those of you who have had chemistry, you've done this already. Alright, so I'm actually trying to get this so this video ends today. Okay, so what do we do with those spent fuel rods? They are stored in pools of water on site. Well, actually, this is the actual reaction area. Why? Because water is a shield from radiation, which is why you can see a dude is right here. So you have to take the spent rods and keep them in lead-lined dry containers on land. So now they're permanently, you know. Now, why don't we shoot these things into space? Take a second to read this. So just realize that although we don't create a lot of waste from nuclear power plants, the waste that we create is forever harmful. Why is it not harmful in the environment before we harvest it? Because it is so not concentrated. Also remember that uranium is a non-renewable resource, and it's really non-renewable. Once this thing falls apart into its smaller components, you can't put it back together again. Okay, we were initially going to, put all of the nuclear waste into one area. Now the pros are, it means you only have one place that you have to worry about, but here are some of the cons. The first part is, whenever you have a mountain, that means that you're sitting near some tectonic plates where they come together. And, you know, obvious problems are obvious when you're sitting close to 2 different plates coming together. And then secondly, as the waste comes towards the mountain, you have opportunities for people to steal it. What can you do with a spent nuclear fuel rod? You can take it, attach it to a regular bomb, and then you have what's called a dirty bomb, which means that you are now exploding Still high levels of radioactive waste across a large area. And then lastly, you are concentrating the components for a nuclear bomb in one place. And from a homeland security perspective, bad. Okay, so I'm sure this is a ridiculously long video, but here is here's the end of this video. So let's go ahead and get you out of here, and have a great day.